Welcome back. In this video, we're going to take a look at a few examples dealing with z-scores and normal distributions. Real quick recap, z-scores, of course, represent the number of standard deviations you are from a mean. So when we say a z-score, it's interchangeable with number of standard deviations to the left or to the right of a mean, depending on that, if that z-score is negative or positive. And we always are going to use this equation. Every time we're going to use this equation. We say z, number of standard deviations from the mean, z equals x minus average divided by standard deviations. And what this represents is x is the value that we're looking at. This is the value we're looking at. This is the average of all values, and this is the standard deviation. This is just a conversion into saying we are this many z standard deviations away from the mean when we're looking at that x value. And we use the z table, which we're going to take a look at in a moment in some of these examples, to be able to convert back and forth between z-scores, number of standard deviations you are from the mean, and a probability. And that's essentially what we're doing every time. Is we're saying we figure out how many standard deviations we are from the mean, and we say, what's the probability associated with being that many standard deviations from the mean? In a normal distribution, if you're far away from the mean, there's a very small probability that's going to happen. You know, if you take a random result out of the entire population of results, chances are it's going to be pretty close to the mean. If it's way out there, you know, there's a very low probability associated with it being far to the left or far to the right of the mean. Okay, so all that said, let's proceed into our first example. If you haven't written this equation down already, do so. So in our first example, I'm reusing a scenario from a previous video. We're back to the telephone call center. In a telephone call center, the typical agent averages 86 phone calls per day with a standard deviation of 11. And management in this company has decided to fire all agents. This is the Jack Welch principle. It decides to fire all agents who are in the bottom 10% in terms of performance. It's a harsh world. What is the cutoff for firing an agent in terms of the average calls per day? So we're assuming in this scenario that the only metric that management is using to evaluate performance is calls. That's it. And so the management has decided to fire everyone who's in the bottom 10%. How are we going to determine who's in the bottom 10% in terms of their average number of calls per day? Well, we can do that because we have a lot of the relevant information here. We have the average, 86. We have the standard deviation, which is 11. But this isn't all that easy. We don't actually know the x value. We don't know what value is the cutoff. I mean, that's what we're trying to figure out. So instead, we have to figure out, using this percentage, the bottom 10%, we need to get back to our x value. So I'm going to write this down real quick. We have z equals x minus 86 divided by 11. And we need to figure out what that z value is. And we can figure out what the z value is by converting it. Like I said, z-scores are interchangeable with probabilities. So we're going to go to our z table to make that conversion. And quick review of the z table. We have our z values, our number of standard deviations from the mean. Along the left, the ones in the tenths places are represented along the left-hand column. And the top row represents the hundredths place. And inside the table, in this middle part, is all the probabilities. So what we're looking for here is a probability of 10%. So I'm going to go searching out that. It's going to be about 0.1. So I'm looking for, and you know, you sort of have to just eyeball this thing. There is a method to it. I'm searching for 0.1. I'm getting around here. It's something. This is as close as I can get, so I'm going to use it. This is negative 1.28. And recall the z table, these probabilities, these are cumulative probabilities, so they represent everything to the left of that z value. In fact, let me make this a little bit more explicit. In terms of our normal distribution, getting better and better at this. sorry. It's, if we say negative 1.28, the probability that's associated with that is everything to the left of that point. So if this is negative 1.28, this value that we got from our z-table is 0.1. 0.1003, but I'm going to round to 0.1 and call it 10%. All right, now we're making progress. So what I've just figured out is that the z-value is actually 1.28, negative 1.28. That is associated with the bottom 10%, right? This value right here, the bottom 10% is over here. The z-score is negative 1.28. So now I just need to solve for x. And I'm not going to bore you with doing the algebra here. What I find out is that x, you can verify this on your own, is equal to 71.92. And whenever I'm doing these kinds of problems, I like to take a moment and just think about this. Does this make sense? Yeah, that 71.92, we can round that to say, because I'm a little bit harsh, 72. If I say we're going to fire everybody who's at or below 72 average calls per day, does that make sense? Yeah, it makes sense. We know that the average is 86, and there's 11 standard deviations, so it's well below 1 standard deviation below the mean. So yeah, that seems like it would probably be around the cutoff point for the bottom 10%. So all those people who have less than 72 calls per day, they're gone. Next example. Monthly sales for a used car fluctuate around an average, let's call this monthly sales for a used car dealership. The used car itself. Monthly sales for a used car dealership fluctuate around an average of 1.5 million. 3 months out of every year, the sales exceed 2 million. And since it doesn't specify which months, we'll assume there's no regularity. It's just randomly, we can expect 3 months out of every year, the sales are going to exceed 2 million. Assuming a normal distribution of monthly sales, okay, what is the average deviation of monthly car sales for this lot? Notice in these examples, I'm not making this very straightforward. I'm playing around with your unknowns. So let's think about this. We have an average. That much is very clear. Average is 1.5 million. And interestingly, we have an x here. The value that we're looking at here is 2 million. But what we don't know is the standard deviation. Who knows what that is? Here's the interesting thing. It says 3 months out of every year, sales exceed 2 million. That's telling me this. 3 months out of every year represents 25%. I think we can all agree upon that. If we did our normal distribution, by the way, I encourage you, that is a terrible normal distribution, but we're going to run with it. I encourage you to draw these out. I don't know that your curves will look quite as tidy as mine do, but it's a very useful exercise because it helps you sort of think about where you want to be, and it helps you verify that your answer makes sense. So what we're saying is, this is 1.5 million. That's the average. At 2 million, sales are going to exceed $2 million. Monthly sales are going to exceed $2 million 25% of the time. Right? 3 months out of every year, 25% of the time. So that can help us get to our z-value. Because if we're 25% is the upper limit, 2 million has 25% exceeding it, that means the rest of this is going to be 75%. Hopefully that makes sense to everyone. Let's go look for 75% in our table. Certainly going to be a positive z-score, and we're close. All right, it's going to be somewhere in between 0.67 and 0.68. So I'm going to call this 0.675 because it's, roughly in the middle. So that's our z-scores, 0.675. So let's set up our equation again. Okay, we know what our z is. It's 0.0675. Our x is 2 million. I'm not going to write out all my zeros. Our average is 1.5 million. And so now we're just solving for the standard deviation. And again, I'm not going to bore you with the algebra. I'll bore you with a little bit of the algebra. Cross multiplying. Oh. Probably you all noticed what I did here. Oh. What a disaster. Make a smaller eraser. I think I can do this. Yeah, it's 0.675, not 0.0675. And solving for that, we get a value of 740,740. That's our standard deviation. So we're saying, all right, if average sales are 1.5 million, and we've solved for our standard deviation, it's about 740,000. That seems to make sense. That says, okay, 2 million is less than one standard deviation away from the mean, but it is certainly over the mean. Therefore, 25% of the sales are going to be 25% of the time, 25% of the months we're going to have sales over 2 million. All right, so we're just solving for different unknowns. We're always coming back to this same equation, which is P and Z. They're interchangeable using the probability, the Z table. And it's Z equals X minus mu divided by the standard deviation. Always using this equation. We're just sometimes solving for different unknowns. There's nothing really to it beyond that. But we're still going to do a couple more examples. All right. Example number 3. Suppose your monthly cell phone plan gives you 1,000 minutes and you get to carry over any unused minutes. You use, on average, 800 minutes per month with a standard deviation of 200. What is the probability that you will exceed the minutes in your plan? All right. Again, most of you are probably reading this and saying, that makes sense. Okay, I can do this. All the same, I still highly recommend you draw out your graph. Even if you're all over this, it's just going to help you avoid silly errors. So our average here is 800, and we want to know the probability of exceeding 1,000, and our standard deviation. So our average is 800. Standard deviation is 1,000. Oh, no. Standard deviation is not 1,000. Standard deviation is 200. And our x in this case, the value that we're looking at, is 1,000. So we're interested in knowing what this percentage is here, right? So let's start out. We've got, so x is 1,000. We're trying to figure out our z value. So our z value is going to be equal to 1,000 minus 800 divided by 200. Hey, that's equal to 1. So our z value is equal to 1. Let's go ahead and use our table. Here's z of 1. And we get 0.8413. So our answer is going to be like 84.13%, right? No, it's not. 84.13, remember, the Z table is giving us cumulative probabilities. This is giving us the probability that the value is anything less than one standard deviation. So it's one standard deviation and less. That's why, I realize not everyone is going to be fooled by this, but it's why I wanted to draw out the graph. And I definitely encourage you to do this, because this helps you say, oh, wait a second, this is a value that is this 1/2, 50% of the values are going to be here, 50% of the values are going to be to the right of 800. This little amount here is got to be less than 1/2, right? And that's when you draw these out, you're always going to know, am I looking for a value that is greater than 1/2, or am I looking for a value that is less than 1/2? And clearly we're looking for a value that is less than 1/2. So actually our answer should be 1 minus 84.13, and that's going to be equal to something like 15.87%, right? All right. So let's start in on number 2. What is the probability that you will accumulate more than 100 rollover minutes? All right. Think about that for a moment. We want to know the probability that we will accumulate more than 100 rollover minutes. Now, we get exactly 100 rollover minutes if we have 900, if we use 900 minutes, because the plan gives us 1,000. Plan gives us 1,000 minutes. So let's just focus on that right now. I'm going to draw this out. My average is still 800. That has not changed. I still average 800 minutes. But now the x value that I'm interested in is 900, right? Because that's the key value here. If I have 900 minutes, I'm going to get exactly 100 rollover minutes because the plan gives me 1,000. Now, I want to know what's the probability that I will accumulate more than 100 rollover minutes. Well, anything less than 900 minutes is going to give me more than 100 rollover minutes, right? I mean, if I only use 500 minutes, I'm going to get 500 rollover minutes. If I, and so forth. If I use 100 minutes, I'm going to get 900 rollover minutes. So clearly what I'm looking for here is all of this. Anything less than 900 gets me more than 100 rollover minutes. Now, this is the exercise here. What do I expect my percentage, my probability to be? What do I expect my answer to be? Well, I expect it to be greater than 1/2, more than 50%, right? Because it's encompassing all of this. It would only take everything to the left of 800 to give me 50%, and there's clearly something else. So let's start in like that. What's the probability that I will accumulate more than 100 rollover minutes? So we're solving for z. Here we got 900 minus 800 divided by my standard deviation of 200. So z is going to be equal to 0.5. And let's go ahead and look in our table. Here's a z value of 0.50. And that's going to be equal to 0.6915, otherwise known as 69.15%. And does that make sense? Is that a value greater than 50%? Yeah, I think this works. So, this is just kind of a sanity check, helps us verify everything makes sense with our expectations. All right, on to the last example. Example 4. A parts manufacturer makes screws that have an average diameter of 5 millimeters with a standard deviation of 0.05 millimeters. A customer needs their screws to be between 4.925 millimeters and 5.075 millimeters with no more than 10% failure rate, meaning every box of screws they get from their suppliers, they can't have more than 10% of the screws that are outside of this range here, 4.925 and 5.075 millimeters. No more than 10% of screws that they receive not meeting their specifications. Will the manufacturer of screws be able to meet this customer's demands without making any adjustments to their current processes? G. All right, let's think about where to begin here. We have some relevant information. Even if right off the top of your head you don't know how to solve this, let's just start putting down info. Well, we've got, I'm going to use blue. We've got an average. Our average size, diameter of our screws is 5 millimeters. And our standard deviation. We've got a lot of good information to go off of right now. It's equal to 0.05 millimeters. And let's forget about, we've got a range that we have to fall into here, right? And let's forget about both sides. I just want to know about one side of the range. So let's think about how this is going to look first of all. I draw a beautiful curve, and then I can't put the line down the middle of the curve. It's very frustrating. All right, so that's our normal distribution. There's our average right in the middle. And our customer is saying, okay, between 4.925 and 5.075, that's the range they want. And you can't have, when you add up this and you add up this, that cannot be greater than 10%. That is not correct mathematical notation. I don't know what the correct notation is, but you know what I'm saying here. Those two parts together can't be more than 10%. In other words, this part in the middle here has got to be 90% or greater. 90% or greater or more of your screws have to be between 4.925 and 5.075 millimeters. So like I said, let's just focus right now on one side of this, because you may have noticed the range for the customer actually it falls nicely on its. In either case, it's just 0.075 away from the mean, and so it's going to be the same on both sides. It's convenient for us. All right, so let's figure out let's just use our x for right now. We're going to call our x 4.925. And let's figure out what this value is right here. So we say z equals 4.925 minus 5 divided by 0.05. Solving for that, we get negative 0.075 divided by 0.05, and so our value is going to be negative 1.5. Let's look that up in our z-table. Negative 1.5 gives us a value of 0.0668. So that's also known as 6.68%. So that's what this is over here, 6.68%. Not looking good for meeting our customers' demands so far. Furthermore, now we'll go ahead and solve this thing, but I know what the answer is right now. I know whether we're going to meet our customer specifications. And the reason I know is because the normal distribution is symmetrical, and in each case they're looking for the same number of standard deviations away from the mean. So let's just work that out. If we use the upper end of their range, it's 5.075 minus 5 divided by 0.05. That's going to be a z of equal to 1.5. Now, a z of 1.5 is going to have the same values greater than it than a z of negative 1.5 would have less than it. And this is a really important principle of the normal distribution and z values. It's going to this is going to make your life a whole lot easier when you're using the normal table. And let's just verify that. We'll go to 1.5. And we see here 0.9332. If you take 1 minus 0.9332, and by the way, 0.9332 is everything, all the values to the left of 1.5 standard deviations above the mean, all of these values are going to be equal to 0.9332. 1 minus 0.9332 is 0.0668. So this value over here is 6.68%. Add those two together, 6.68% plus 6.68%, also known as 6.68% times 2, is going to be something, but it's bigger than 10%. So are we going to have a greater than 10% failure rate? Yeah, we are. More than 10% of our screws are going to fall outside this range. Therefore, can we meet the customer's demands using our current processes, the way we manufacture screws? No, we cannot. We cannot meet that customer's demands.